Hi, tonight I want to talk about Peltier devices, or TECs, thermoelectric coolers. But we're going to shift gears. We're actually going to throw this into reverse, and we're going to use these devices as TEGs, or thermoelectric generators. If you're interested in the deep principles behind these, take a look at the video that we did a couple of months ago on the solid state refrigerator. In all of the videos that we have done so far using these devices, we've used them as heat pumps. By using electrical energy, we can create a temperature differential between the two faces of these devices. But the process can be inverted, and you can actually create a voltage and thereby a current if you create a temperature differential. If you take a look at this voltmeter that I have here hooked up to one of these devices, take a look at what happens to the voltage on there if I just take my warm fingers and touch the surface. We create a voltage. Take a look at what happens if I change the direction from heat to cool table, and now hot fingers to cool air. We change the direction of the current. What's interesting about this is how sensitive these things are. If you take a look at this, and after it stabilizes a little bit, I'm going to put my warm fingers in front of, but not touch the surface. Just get them close. And you can see without even touching the surface, I'm about 3 or 4 millimeters above it, I can actually create a voltage. Now, because my hand is above the surface, any convective currents are rising. And it's the 10 to 15 micron thermal radiation from my fingers that's sufficient to create a noticeable voltage here. A few years ago, we actually took about 64 of these things and created a very low resolution focal plane array. You can actually create an image with these devices. It's kind of kludgy, but it does work, so they're kind of neat. What's fascinating about that capability, though, is that these devices will allow you to harvest heat energy, even at very low efficiencies, 3 or 4%, from what would otherwise be unavailable thermal differentials. For example, my skin. You could produce wearable electronics with these devices. In addition, you could take, say, just unconcentrated solar heat, create electrical power. You can put an array of these things and stare at the clear night sky, which is over 100 degrees below zero thermally, and the temperature differential between the air and the night sky can create electricity at night. You could generate power from sewage, from the low-grade heat that comes off of, say, the flue from a residential furnace. The only other system out there that has the potential to do anything like that is, say, a Stirling heat pump. The problem, though, is those are rather delicate and they're a little bit complicated. Well, this device is solid state, no moving parts, very robust, very light. If you're thinking about using this kind of a device, you might be tempted to buy a TEG specifically designed for this purpose. This device here, which is a little bit bigger, contains the same semiconductor diodes that create the thermoelectric effect as in the smaller device. But because it incorporates higher temperature wiring, higher temperature solder, this device has a maximum hot side temperature of about 330 degrees centigrade, while this one is limited to about 150 degrees centigrade. However, at the same temperature differential, these are equally efficient or inefficient. The difference, though, is that these 12710 TEGs are available on eBay for about $2.50 each, while this bigger device here is going to cost you about $50, about 20 times as expensive. Now, there is an advantage for the higher temperature differential. You'll produce more power. In addition, when you have a higher temperature gradient, you will produce that power more efficiently. So this makes a big difference. But whenever you're using these devices, you have to regulate the hot side temperature, because even though these can get hotter, you can still damage them. And if you're going to put this, say, on the side of a wood stove flue, or you're going to use an oil boiler to get this thing up to temperature, you're going to have temperature regulation incorporated. What we decided to do is, because we can use boiling water, 100 degrees centigrade at sea level water, as our temperature regulator, we've decided to go with these devices despite the slightly lower efficiency, because they're so much less expensive. So the device or the system that we built here depends on these other components that you can get on Amazon and on eBay very inexpensively. It's about $3. They come in a variety of different sizes and shapes. And these are simply water cooling blocks. And they are typically built around the 40-millimeter dimensions of these most common 12710 chips, so that you can easily place the block, use thermal epoxy, and place this on the surface to get nice thermal contact. If you flow water through one side and then, say, have a heat sink on the other side, create a temperature differential, you can create a current. You can also cool a computer chip with this. Because these are so inexpensive, and because of the fact that we can use these, both sides of these, what we decided to do is, in our little test module here, we took 2 of these TECs, or in this case TEGs, and thermal epoxied them on either side of the cooling block. And then, running ambient cool water through the center, we then immerse the entire device in hot boiling water to create the temperature differential. So let me show you how this works. If you look here, this is a temperature probe. We're going to dip this in. You look here, and this is the voltage that's being delivered by this device to the volt ohm meter directly. So there's no load on this. Lower this down. You see the temperature quickly rises. We're a little below boiling, but we're getting close. Now you look, and without any kind of a load, we develop about 5.3 volts. Now, because I have both of these TECs wired in series, each one's developing about 2.7 volts. And you can mix and match depending on what kind of voltage you want as an output. But in this case, we decided to series wire them. An important thing you'll notice too is the typical standard of wiring is that red positive, ground negative, black. But because of the nature of how you are placing these devices across and heating, you may sometimes be fooled by which is going to be the positive and negative side. So whenever you build one of these devices, you probably want to test it before you do the final wiring, just because it's going to make sure that you don't screw it up once you glue everything together. So although this looks like I've got this in a dead short, I don't. This is actually operating in series. Now if we look over here, I have some resistors. And the purpose of the resistors is to apply a varying amount of load so that we can determine if there's an efficiency between the mixing of voltage and current draw. Right now, no current draw, we're just driving a meter. Now these are 2 ohm resistors, and I have them wired, in this case, in series. So if I connect this up here, I've got 2 ohm plus 2 ohm, 4 ohms. So whatever current I develop is going to be 1/4 the voltage that I see. So in this case, I'm developing about 3.1 volts. So I'm developing what, about 760 milliamps in this case. So about 3/4 of this voltage in power. So I don't know if we can calculate that, but it's going to be about 2.5 watts, something like that, 2.4 watts. Now what's interesting is keep an eye at what happens when I change the current draw on this. Right now, as I said, in series, if we then just take off the 1 resistor so that we go to a 2 ohm setup, just 1 resistor, the voltage now drops down to 2.2 volts, therefore 1.1 amps. So right now we're generating about 2.3 watts with the 2 chips. And if we then decide to go to a simple 1 ohm resistor, 2 ohm resistors in parallel, so the voltage and the current will be equal, we see we're down around 1.4, 1.44. So therefore we're making a little less than 2 watts. Temperature is the same, everything about the setup is the same, and what that means is that when you are going to be wiring these things up to use them for power, there's going to be a curve, an optimal broad, but curve in terms of developing the maximum amount of efficiency when you're setting this up. So if you put a module together with multiple chips, You want to keep in mind what kind of voltage you think you're going to need so that you wire it up so that it will generate the optimum amount of power. In this case, it turns out that that curve favors the higher resistance. You want a relatively high voltage. And as we saw, about 4 ohms for 2 of these devices for this particular device is optimal for the 12710. Now, as you can see, we're making about 1.2 watts or so per device, and we're not even at boiling, and we're at a relatively warm room temperature. If we were doing this in a colder environment, we'd probably get up to around 1.25, maybe 1.3 watts per device. So with this success, we decided that we would go ahead and we would get a larger module put together, and let me show you that. All right, so when we constructed these things, one of the things that I did is to inhibit the heat flow from the sides through the boiling water into the side and the back surface potentially of the Peltier devices. I fabricated these aluminum screens or aluminum frames, just sawed them out and sanded them smooth, and then put 2, one on each side of the block. And then by filling up this gap with insulating plastic and foam, I prevent any of the water heat from getting to the insides and essentially making them even less efficient than they already are. Now, I've already done this side and I've done this side, but I've left this exposed so you can see that this is a 2-part urethane foam that covers much of the surface, provides the good insulating capabilities, and then we're going to cover this with a little bit of a 2-part silicone oil or silicone potting material from Silicone Solutions. This material is really nice. I'd recommend it. It's about $20 for about 600 grams. That's enough for about 6 of these things. And it provides a very tough, waterproof surface so that you don't damage the foam. And as you can see in some of these witness or experiments that I did, you can see it's about half rubber and half expanded polyurethane foam inside the channels. It's a white, creamy, milkshake-like, yogurty sort of consistency, has no aroma. And I'm going to go ahead and put 60 grams into the cup right now. And once we do that, then we're going to put in the catalyst. Now, the catalyst can be added from anywhere from 3% to 5%, and all that does is change the cure time. I'm going to be running this at about 4% just to kind of split the difference. So it's 3 to 5% by weight. Good. So we're going to add 3 grams of this, or 4 grams, 3 grams to be essentially 5%, and about 2 grams to be about 3%. So maybe about 3 grams would be somewhere in there. It's not going to have to be that accurate. So let's look for about 64 on this. This is a little thinner in consistency, and because of the dye, it helps you to know that you've blended it because you'll see all the stripes as you're beginning to mix it. Now we're looking for 64 on this. And as I begin to mix this, you'll see that the blue begins to incorporate and you start to get more of a cyan color. But you'll know that when you've got it fully blended because you get the same sort of light blue color that you got on the witness sample. The material that I'm using here is actually in a couple of cups over here. You see it looks like honey or maple syrup and has about the same viscosity. When you blend these up in a 1-to-1 ratio, you've got about 1 minute, and then they begin to expand, but they form a foam that is much denser. It has a very high thermal resistance, and also much, much stronger. You really can't dent it even with a thumbnail, and you could put screws into it. So it's kind of a nice material, and because it doesn't expand like crazy for 20 minutes, it tends to be a lot easier to work with and more predictable. Now that I've got this nicely blended up, and you can also take a look at the outside to see if you missed any areas, but this looks pretty good. So now what I'm going to do is, in order to prevent some of the bubbles that I got in my early examples, I'm going to take a syringe and I'm going to put it deep into the mixture, and then I'm going to pull out until I get the full 12 cc's in here, and then place a little industrial non-beveled needle on the end of this. And the trick is to put it in at a very thin amount. The idea is I want the bubbles to be able to rise. I don't want to fill this up rapidly and then be dealing with bubbles for a long time. So patience is best here, just to coat it and give the blue a chance to kind of get into the gaps and let the bubbles rise only a half a millimeter to get out. And now I can be a little more aggressive and just let it fill in here. And this is why it's important that you level it, because it'll kind of naturally just find a nice surface there. OCD, maybe. And that's it. Once these cure, give it about 2 hours and this stuff will rubber up to the point where you can turn this over and it won't change its shape. And then in about 18 hours, it's as firm as the material that I showed you there, where you can make a dent with your thumbnail, but it doesn't cut it. And then at that point, then we'll go ahead and we'll turn this over and I'll do the final side with the rubber tubes that are actually going to be on the module, sticking out through this on the bottom and connecting up to the manifold that's going to distribute all the cooling water in between them. But we don't want to turn this over until this is set up. In this particular model, each of these 12 TEC modules is wired up so that they are all in series within a module, and in this case, wired in series between modules. So we're actually running 36 of these TEGs in series, and obviously we'd be able to produce over 100 volts without a load with this. But we decided that that was about the right voltage based on the current that we were going to apply for the application that we were going to use to test this. So the big question you have to ask is, did it work? So originally what we were going to do is test this and demonstrate that it really works by placing this generator into a pot of water on top of a burner inside the lab, and then cool the inside of the generator by using the radiator system, the same one that we use for our brewing video. But that's not as much fun as actually taking this thing out into the real world. So because we live in a very mountainous area and we've got a lot of streams, what we decided to do is find an area where we could run some tubing upstream about 30 meters, about 100 feet, and as a result, we generate a nice flow of water without having to use any pumps, and continuous flow basically for free. The water generates a head of about 2 meters or about 6 feet. You see it cuts off right about there. But that's plenty of pressure down here to be able to cool off the generator. And then what we're going to do is we're going to exhaust the warmed water by simply dumping it back into the river. So we're using the river water as a free heat sink. Water comes in, water goes out. And then to heat the pot, what we're going to do is we're actually going to build a little campfire. Now, even though these generators are very inefficient, say 3–4% tops, the point is you're never going to run out of fuel. And so if you decided to take this camping or you brought this to a cabin, you don't have to bring any gasoline, you don't have to worry about any consumables. Conceivably, this thing would run for years without having to invest anything or to lug anything into your campsite. Obviously, you're going to have to replace the water that's eventually going to be boiling out of your container, but you got plenty of that. So first thing I'm going to do is I'm going to start the fire, get that thing revving up, and then as it continues to get darker here, I'm going to set up a little tripod to support the tubes so that everything stays nice and controlled, nothing gets overheated, we don't burn our rubber tubing. So let's get started with the fire. All right, so now I'm going to fill this up with a little bit of water. Ready? Here it goes. Now this is obviously a little campfire, and it's, you know, temporary and initial setup of the prototype, but if what we were going to do is we're going to set this up for a long-term burn, what we might do is we might want to put some sort of a metal structure over here so we can hang the pot from a good distance up. Therefore the tubes go way above the fire. We really wouldn't be concerned about the little tons of flame licking up against, say, the tripod or the wire or the tubing. But for a little portable setup, this isn't bad. Now this is a pre-3590 4000K light, so it's pretty close to sunlight. And as you can see, the light itself is pretty steady because obviously the electricity that's running through here is just DC current, and the water is a very stable source of it. So we don't get any flickering, we don't have any electronic controls, we just simply have wires. It's easy to set up, it doesn't require any kind of electronic skills, just some woodcraft. Okay, so even though I've let the fire die down a little bit, the water stays hot for a fair period of time, simply because of the cold and just the residual heat in the water. But at least you think that this thing actually is not generating heat from the temperature differential. I'm going to take this out and just show you how effective this actually is. So I want to thank you very much for watching. Please subscribe because we got a lot of interesting videos coming up. Some of them inside, some of them outside. But all of them should be pretty interesting. Take care and have a good night.